Okay, now this example really isn't conceptually any different than the previous one, so I'm going to go a little bit faster, but we're going to do essentially the same strategy. Okay, so we've got a function, again, it's called t, that's fairly common. Our domain is R2, so the input vector has to have two coordinates, and sure enough in the formula you can see this two-dimensional vector that appears as the input vector here. The codomain is R3, so the output vector had better have three coordinates, and according to this rule, it does. So that everything looks good, right? We want to show that it's a linear transformation. So we're going to start by picking two arbitrary vectors in the domain. And just to be consistent with last time, I'll call them u and v, but really I could call them whatever I like. I don't need to call them u and v, right? As long as I pick labels and I'm consistent, that'll be totally fine. So I got my two vectors in R2. And I want to show that t of u plus v is the same as t of u plus t of v. Okay, so let's start by adding the vectors u and v together. So we'll have u1 plus v1, u2 plus v2. And note, I haven't even really looked at this yet because I don't need to until now, but now I do because I want to actually apply t to the result of this addition. So let's take a look at what happens. So t, it looks like t for the first two coordinates, it just takes a copy of the two coordinates of the input vector, but then for the third coordinate, it takes the sum. Okay, so our output vector here is going to look like the following. I'm going to try to leave enough space. We'll have u1 plus v1 for the first coordinate, u2 plus v2 for the second coordinate, and then we'll have the sum of those two coordinates for the third coordinate. And I didn't really, much as I tried, I still got the spacing wrong, so I'm going to cheat and fix it, okay? All right, so that's t being applied. Now I'm going to reorganize the terms and get ready to decompose this. I don't need to do much for the first and second term because they're already about as organized as they're going to get. For the second or the third coordinate, I can get the u's together. I can write this as u1 plus u2 plus v1 plus v2. And then now I'm ready to split this up nicely. I can write this as u1, u2, u1 plus u2. That's taking care of all of this material here. And then the other vector I'll use to take care of all this material. So plus v1, v2, v1 plus v2. Okay? And this worked out perfectly because this is exactly t of u1, u2. And this one is exactly t of v1, v2. And that's just the same as t of u plus t of v. I could have even actually skipped this step, to be honest. I didn't do that last time because I kind of mentioned it when I made these annotations here. But I could have just went, there's nothing wrong with going right from here to here because you've already said what u and v are. But in any event, there's also nothing wrong with writing that extra step. So I'm going to group this now. This is the justification that condition 1 is satisfied. Let's verify condition 2. So remember, we're going to take an arbitrary vector in the domain. So let me write, I'm going to write it as u1, u2 in R2. So that's an arbitrary vector. Remember, the vector, when you, I'll use the word summon. You're kind of just saying, okay, let's say we've got two vectors, right? Suddenly they're there and you've got them on the page. And say I'm doing that here as well. I'm always going by the domain, right? That's how I know how many coordinates to give to each of these vectors. If this were R4, if the domain were R4, well then these vectors would all have 4 coordinates. But then you'd also see 4 coordinates here as well. But anyways, you don't. So that's, in this case, our domain is R2, so we have 2 coordinates for our vector u. But then we also need a scalar for this second condition, right? Because we're trying to show that t of c times u is equal to c times t of u for every vector u in the domain and for every scalar c. Okay, so let's go ahead and start with t of c times the vector u. Well, by definition, multiply the vector u by c, you're going to get cu1, cu2. Okay, and then when we apply the transformation t, we're going to get cu1, cu2, cu1 plus cu2. Where am I getting that from? The rule that defines the function t, right? I'm just using that rule exactly. Okay, and then I can say, all right, the third coordinate has those two terms in the third coordinate have a common factor of c. So I can write this as cu1, cu2, cu1 plus u2. And then I can pull out the c. So I've got c times u1, u2, u1 plus u2. And that is exactly, this vector is exactly t of u. Right, so this is actually, since I only have a space for one more step, I'm just going to write is equal to c times t of u. Okay, so that's the completion of our verification for the second condition. Okay, so now we can draw our conclusion and say, therefore, t is a linear transformation. And if you see these two examples back to back, I went a bit quicker through this one, but if you compare them, you'll see that they kind of have that same format. There's those two main steps. You're verifying condition 1, verifying condition 2. Same thing here. We verified condition 1, verified condition 2. They all kind of have these specific pieces where you start by grabbing your vectors, and then you work the left-hand side of each equation into the right-hand side. Here we started by starting with our vectors as we needed, or one vector and a scalar. We work the left-hand side into the right-hand side. I'm talking about the left and right-hand side of these conditions, right? That's the idea behind these proofs. They all follow a similar format, and the more you practice them, the easier they get.